Добрый вечер, уважаемые друзья, коллеги. Рад вас поприветствовать от лица компании Microsoft. Меня зовут Алексей Паладин, я директор по работе с фондом Сколково. Особо хотел поприветствовать всех студентов Открытого университета Сколково. Если можно, поднимите руки, кто нынче слушатели Открытого университета. Двое, трое. Остальные-то кто? Надеюсь, тоже московские студенты, которые пришли послушать интересную лекцию, а также представители стартап-комьюнити и все те, кто заинтересованы в том, что с чьей-то легкой руки называется облако. Облако – любопытная вещь, которая на самом деле облаком не является. И для нас сегодня большая честь представить вам, нашего дорогого гостя, доктора Дилипа Бхандаркара, ведущего сотрудника и главного архитектора Global Foundation Services Microsoft. Я передам слово для представления моей коллеги Ксении Болинской, которая работает в Открытом университете Сколково. Она вам немножко расскажет о заслугах Дилипа. Пожалуйста.
Раз, два. Стало слышно. Здравствуйте, друзья. Я Ксения Болинская, Открытый университет Сколково. Очень рада вас здесь приветствовать. И мы также наши любимые партнеры компании Microsoft благодарим за то, что мы смогли сделать эту лекцию. Дилип, как я недавно узнала, на самом деле, обладатель 16 патентов США в области компьютерной архитектуры. Также, если вы читали, он написал множество, более 30 технических статей и также написал книгу по системам Альфа. Очень интересно, что Дилип начинал свою карьеру программиста с изучения советской машины. Вы знаете, Минск-2, для этого ему пришлось изучать кириллицу, поэтому, возможно, пару вопросов на русском он вам ответит.
Какую машину он изучал?
Простите?
Какую машину он изучал?
Минск-2.
Минск-2.
So I worked on the Minx-2 before most of you were born.
Да, собственно, Открытый университет Сколково и компания Microsoft представляет вам замечательного человека Дилип Бхандаркар.
И мы сейчас передадим слово Дилипу. Лекция будет на английском языке. После лекции будут вопросы и ответы. Если вам удобнее задавать вопросы на русском языке, пожалуйста, задавайте, мы с удовольствием переведем на нашего гостя.
Повторный перевод будет во время лекции?
Нет, лекция будет на английском языке.
А что не было написано на сайте?
Да, это было опубликовано на сайте, извините, но будет на английском языке. Так что передаем слово Дилипу.
Thank you. It is indeed a great pleasure for me to come back to Moscow again. This is my fourth trip here, and I always enjoy being here. In addition to the first computer that I ever touched was a Minsk-2, I've also worked with a lot of Russian engineers over the years, both people working in Russia as well as people that have moved to the U.S. So I have a lot of respect for the talent that's in this room. I'm sure you'll all be doing some great things over the next few years. I'm going to give you a quick overview of the cloud infrastructure that Microsoft is building for the online services that Microsoft provides. My group supports more than 200 different online services at Microsoft. Here are some of the names, some names you might recognize: Windows Live Messenger, Bing, Hotmail, Xbox Live, Windows Azure, let's see, Office 365, lots of different services that we support. So we have to support lots of different usage models, a lot of different groups with different requirements. And we do that at a very large scale. We have to support it on a 24/7, 365-day basis worldwide. And we have some very large volumes. You can see 300 million users, 500 million users, 4 billion Bing queries. So it's a fairly large operation worldwide. In order to support that, we have more than 10 large data centers spread worldwide to do that. And this just shows some of our bigger data centers. If I tried to show all of them, there wouldn't be enough space to do that. And typically what you see is we like to build data centers that are somewhere in the 30 to 50 megawatt range. And in each of the facility, there are some unique characteristics. Our data center in Quincy, Washington, which is about, let's say, how far is it? About 200 kilometers east of Redmond and Seattle, was the first one that Microsoft designed and built. We use hydroelectric power there. In our San Antonio data center, we use recycled water. I don't know whether you're aware, but a typical data center uses millions of gallons of water during the year. So you don't want to use drinking water because that's something that you want to use for people to drink. So this is recycled water. This is the water that people use to water their gardens and etc. that gets recycled and maybe cleaned up a little bit, and that's what we use. And then similar other things. In Dublin, we use 100% outside air cooling. So there's no air conditioning, no refrigeration. We just bring in outside air. Fortunately, the weather in Dublin is such that the outside air never gets any warmer than 25 degrees centigrade, so we can use outside air year-round. So with all these data centers, they have to be connected. We have our own fiber inside the US. We also lease capacity from other providers of network bandwidth. And as you can see, our network has grown over 10x in less than 5 years. So it's a large operation, lots of, multiple terabytes of capacity that are being used to serve customers worldwide. Now, when you think about the data center, how many of you think that that's what a data center looks like? I mean, that's what you walk through when you go see the servers, right? And that's only part of it. In order to support that, it takes a lot of other equipment, expensive equipment that is then used. There are batteries, generators, substations, cooling towers, chillers, and lots of pipes and things that are part of the cooling system. So if you look at a typical traditional data center that's built in a regular brick and concrete kind of building, that's what it looks like. The picture on top is our Chicago data center. The one on the left is our Quincy, Washington. That little building behind our data center is a beer distribution storage place. Just happens to be that way. There's no connection to the data center. We don't use beer to cool the servers. But typically the size is about as big as 11 football fields. And as I mentioned, 20 to 50 megawatts. And it's very expensive. It costs anywhere from $10 to $15 million per megawatt in capital equipment. So this is the data center with all the cooling, the electrical distribution, not including any servers or network equipment. So this is just the cooling and power infrastructure. And then it takes 1.5 years to 2 years from the time you start construction to the time that you can bring in the first server. This long delay causes a problem because you have to know 2 years in advance how much capacity you're going to need, and it's very hard to predict what you're going to need. So over the last few years, we've looked to do two things. One is bring this cost down closer to this number than that number, and reduce that time by a factor of 2. So today we can bring on a new data center in 9 to 12 months. And we have much higher confidence in being able to predict how much capacity we're going to need 1 year away than we can 2 years away. Why is that important? Because if you build too much, then you've got this expensive data center with nothing in it. If you build too little, then you don't have enough capacity to serve your customers. So you have to get it just right. So when I talk about that $10 to $15 million, where does their money get spent? The least expensive part is the land itself, at least in the US. Now, when you go to Singapore or Hong Kong, the land is quite expensive. And it's about maybe 0 to 2%. If you're lucky, somebody might give you land for free, right? But usually you have to pay to buy the land, but that's not that expensive. The building itself is maybe 5 to 10%. Most of the expenditure is in the mechanical and electrical system. That's cooling, power delivery, and power distribution. So if you continue like this in adding new capacity, the place where you want to pay a lot of attention is to reduce the biggest piece. So we've been working to reduce that 70 to 85% number down to something more manageable. Now there's also another important piece. Have you heard about power usage effectiveness? Everybody know what that is? No. Let me tell you what it is. PUE is the total power consumed by the data center divided by the power consumed by the IT load. So if I say my PUE is 1.6, what that is saying is for 1 watt that's consumed by the server and network equipment, there's 0.6 watts that's either lost in the power distribution or consumed for the charging the batteries, or consumed by the cooling system, the fans, the pumps, and the cooling towers, and all of that. And the industry average for PUE, at least in the US, is about 1.8. So it's, and a lot of this is because of older data centers. Our average today across all our data centers is less than 1.5. On some of our newer data centers is less than 1.2. So if you look at the 3-year total cost of ownership, the blue part is what I paid for the server. So let's say I paid $2,500 for a server. This is just an example. And say it was 200 watts. Now, most of the time you just think about what you paid for the server. But over the 3-year life, it's going to consume electricity. So this orange-brown part is what you have to pay the electric company for the power that you use to run that server. This light green part is really an allocation of the capital expenditure, the depreciation on the data center itself. So if it was 12 million per megawatt, I take that and say, how much of that is allocated to the 200 watts? You just do the ratio, and then that's that piece. We depreciate our data centers over 15 years. So if it was 15 million, it's 1 million per megawatt depreciation for the whole data center. And again, part of that needs to be allocated to that server. So if you add all those numbers then, if for every watt that a server consumes, it costs about $1 to $3 per year. So what that says is that if I can reduce the power of a server by 1 watt, and it costs me $0.50 to save that power because I'm using more efficient but more expensive components, it's 50 cents more for a more efficient power supply, let's say. I'm saving $1 to $3. It's a good decision to make to spend a little bit more on the initial purchase because over the life of the server, you're going to save money. It's just like saying that you might pay a little bit more for a car that gives you better gas mileage. Same idea. So if you look at Microsoft's data centers, we started building those in 1989. Well, actually, we weren't building those. We were leasing space in somebody else's data center where you don't have control over the environment. So and they don't have control over your IT equipment. So the PUE in some of the old data centers is 2 or even higher in some places. As we started building our own, we were able to drive the PUE down. with each successive generation. And with our fourth generation data centers, where we're using mostly outside air, we see PUE anywhere from 1.05 to 1.15. On a cold day, it's closer to 1.05. On a hot summer day, it's closer to 1.15. Okay, let's see if I can make this video work. This is a tour. How many of you have been inside a data center? Okay, so this should be fun for you to watch, unless you've already seen it on YouTube.
Where is the Microsoft Cloud? In reality, it exists in our vast worldwide network of data centers that provide the foundation for a wide array of online services. When you use one of these services, for example, to do a search query on Bing, your request travels from your PC or mobile phone across the internet connected by an extensive global fiber optic network through our content delivery network nodes, moving at the speed of light to a data center that executes the query and returns the results, all in a fraction of a second. Microsoft's cloud is comprised of a globally distributed data center infrastructure supporting over 200 online services. More than 1 billion customers and 20 million businesses in over 70 countries use these services each year. Today, we're going to take you on a tour of a few of our data centers and show you how Microsoft's Global Foundation Services team, the team that designs, builds, operates, and secures our cloud infrastructure, is delivering high availability and reliability, high efficiency, smart scalability, a secure, private, trusted cloud, and sustainability in all our facilities worldwide. Microsoft has been operating data centers since 1989, and this is an area where Microsoft continues to make significant strategic investments. From 1989 to 2004, our data centers were built to address early computer systems that required controlled temperature environments in which to operate. From 2004 to 2007, we began to design our own large facilities to provide our online services with a range of solutions for more rapid deployment and more efficient operations. In 2007, we opened our first Generation 2 data center in Quincy, Washington, which began to change the industry standards for large-scale internet data centers. Today, the facility is approximately the size of 10 football fields and houses tens of thousands of high-performance processing and storage servers in high-density racks that are separated by hot and cool air aisles on a traditional raised floor. Chillers and air handling equipment ensure precise control over environmental conditions. Uninterruptible power supplies, or UPS systems, and vast banks of batteries ensure electricity remains continuous in the event of a short-term power disruption. Emergency generators provide backup power for extended outages and for planned maintenance, and can operate the data center with on-site fuel reserves in the event of a natural disaster. A high-speed, robust fiber optic network connects this data center with other major hubs and internet users. Edge compute nodes host workloads closer to the end users to reduce latency, provide geo-redundancy, and increase overall service resiliency. A team of engineers work around the clock to help ensure services are persistently available to customers. This facility is powered 100% by renewable hydropower. To deliver cloud computing services for global businesses and consumers within a very cost-effective and sustainable operation, we evolved our data center design strategy. Traditional data centers take from 18 to 24 months to build. With our modular approach, we work to reduce costs and deployment time while increasing overall efficiency and sustainability. In 2009, we opened our Chicago data center that spans approximately 10 football fields in size. It is a Generation 3 facility and was our first deployment of modular computing units to dramatically reduce infrastructure costs and the time to deploy large volumes of compute power. We used standard shipping containers to house up to 2,400 servers that were trucked on site and plugged into power, water, and networking infrastructure already in place. This enabled us to scale out capacity to meet customer demands for services within hours versus weeks, and significantly reduced packaging materials, transportation waste, and carbon emissions. Another green IT approach is the use of waterside economization, which enables us to cool the facility without requiring the high levels of electricity typically needed to power large chillers. Power usage effectiveness, or PUE, is the measure of total data center power consumption divided by IT, or critical power, and highlights how much power is consumed by supporting infrastructure versus the power to operate servers. A typical industry data center has a PUE of approximately 2.0, where the amount of energy consumed for the facilities and supporting infrastructure equals the energy to power the servers. This award-winning data center has a PUE from 1.15 to 1.22 for the containers in the facility. Also in 2009, we further developed the containment approach to deliver additional efficiencies in our Dublin Generation 3 facility. This facility spans approximately 7 football fields in size and deploys large-scale compute capacity contained in pods of servers cooled by airside economization. Air handling units on the roof draw in cold outside air to provide the cooling for the servers and facility. Evaporative coolers, vaporizing water into the air to absorb heat, and an air bypassing feature improves operational efficiency and maintains constant room temperature, regardless of outdoor conditions. The facility uses less than 1% of the annual water consumption of a traditional data center. Our Dublin facility maintains a PUE of 1.25 and improves energy efficiency by approximately 50% as compared to our traditional data centers of similar capacity. In 2010, we began to build our first Generation 4 data center design, building on the Dublin experience of using airside economization into a truly modular design. This technologically advanced facility challenged every industry design standard to significantly reduce water and power use, and it uniquely demonstrates how we have evolved our approach. Our Generation 4 facility utilizes air-cooled, IT pre-manufactured components, or IT packs. These state-of-the-art pre-assembled plug-and-play modular components can be manufactured in many locations through a dynamic supply chain of globally distributed vendors and use recyclable materials such as steel and aluminum, which are then shipped on-site and assembled. IT packs allow rapid commissioning of additional compute capacity as the business needs it, reducing the typical 2-year construction timeframe in half and reducing capital costs by 30 to 50% over the lifetime of the facility. The IT packs also provide self-contained UPS, along with air handling and evaporative cooling systems to control ambient temperatures, with 4 cooling modes to ensure the inlet temperature is maintained between 50 and 90 degrees Fahrenheit and 20 to 80% relative humidity. Our simple recyclable metal building provides shelter from weather and directs proper airflow through all systems. This approach enables us to deliver PUEs of 1.15 to 1.2 across the facility, and energy is provided from 100% renewable hydropower. Operational excellence and services reliability comprise our highest priorities. Microsoft ensures high availability through advanced monitoring and incident response, service support, and backup failover capability managed through our geographically distributed Microsoft Operations Centers, operating 24/7/365. We also deploy one of the largest implementations of Microsoft System Center in the world, and we use our own data center repository called Scry to record power consumption and allow precise cost allocation to our internal business groups. In addition, our network is one of the largest in the world, with a fiber optic and content distribution network backbone connecting our data centers and edge nodes to ensure high performance and reliability. A large geographically distributed footprint of data centers enables us to be close to customers to reduce network latency and allow for geo-redundant backup and failover. Security at our data centers employs outer and inner perimeters with increasing security at each level, utilizing a combination of technology and traditional physical measures. Technical elements include 2-factor access control, badge readers, extensive camera monitoring, and integrated alarm systems. Traditional measures can include perimeter fencing, security officers, and locked server racks. Data secured in Microsoft's data centers is classified based on its value and protected accordingly. For example, hard drives with highly sensitive information are routinely destroyed when they are decommissioned. We also limit access to our facilities and servers to only those individuals who have valid business needs. In addition to maintaining best-in-class operations processes, we routinely bring in third parties to verify our capabilities, resulting in ISO and PCI certifications, SAS 70 Type 2 attestations, and FISMA certification and accreditation. Microsoft's award-winning cloud infrastructure powers the cloud services our customers and partners use every day. So the next time you search on Bing, expand your customer services with Windows Azure, communicate with employees via Office 365, email your family on Hotmail, or challenge your friends across the world on Xbox Live, you too are tapping into the power of the Microsoft Cloud.
Okay. So what are some of the challenges that we face and other companies that are trying to provide cloud services with respect to data centers? Well, first one is that it's a large capital expense. You spend a lot of money up front, and then it takes you 2 to 3 years to fill out the data center, and that makes it very difficult. So our answer to that problem is to build modular data centers and add capacity in small chunks, maybe 2 megawatts or 4 megawatts instead of building the entire 30 megawatts all at once. How do you scale globally? Where's the demand going to be? Where do you need to locate your data centers to provide the kind of latency that your customers require, the kind of performance they need? How do you handle the fact that the demand can be up and down? How much extra capacity do you build for? And then the other issue that we've been spending a lot of attention on is reliability or resilience versus cost. If you build a highly reliable data center, it's not 100%, and the cost goes up quite a bit as the reliability level goes up. So we're moving a lot of the reliability part into the software. So we're asking our software engineers to write software that can run in spite of failures in the hardware infrastructure. So if something fails, you want to be able to quickly move the load over to someplace else, and that someplace else needs to have a copy of the data that's accurate and consistent with what you were trying to do. And then reducing the total time to market, which is, I said, we want to bring on new capacity in 9 to 12 months instead of 18 to 24 months. So if you look at our future data center, and actually this slide is pretty old, so the future is now. So the data centers that we're building today, we don't worry so much about square footage, because as you saw, the building itself is 5 to 10% of the cost. So you want to make sure that you have enough floor space to accommodate all of the racks that will consume all of the power. So you don't want to run out of floor space before you use up all of the power. So we focus everything on how to optimize using all of the power that you paid all this expensive cooling and power distribution for, and then drive down the cost of that infrastructure. By using outside air, we've reduced the cost of the cooling system, and then the electrical distribution system also, there are ways to reduce your costs. By using pre-manufactured components, and standardizing, so you're buying more of the same instead of doing something different every time, that helps you reduce your overall cost and helps you bring on new capacity faster than if you are doing custom build, custom design every time. And then we have some applications can tolerate lower reliability, lower cost. There are some older applications, enterprise applications that require high reliability. So instead of forcing everybody into the high reliability, we are essentially building two flavors of data centers, some of them on the same site. So one room maybe or one building could have availability of 0.999939 because the application requires that reliability. But then there are many other applications that can tolerate 3 nines reliability, 0.999, 99.9%, which is less expensive. So for those applications, we build a less reliable, I wouldn't say unreliable, but less reliable data centers to save money. So the other thing is we measure everything that we build, monitor the performance, look at what's working, what's not working, and then that becomes the data and information to improve the next time. And then the basic principle we have at Microsoft is challenge everything. Don't do things the way people have done it for the last 15 or 20 years. Lots of times people say, oh, we have to do this, and I ask them why. Oh, because that's what we've been doing for the last 25 years. Well, it's a different world. It's a different scale. Applications are different. So we say, challenge everything. Don't let somebody tell you that you can't do it because it hasn't been done. If we did that, then we'd still be riding, horse-drawn carriages, right? We wouldn't be driving around in cars and flying in airplanes. So we take that to heart and we try and do some innovative things to improve the efficiency, drive the cost down. So here's an interesting story of how our Dublin data center has evolved. The first construction was in 2009. That's the building on the top, that gray building you see. It's a typical brick and concrete construction with lots of steel also, reinforced concrete, 2 floors. The computer rooms are on the second floor. The bottom floor has a lot of the electrical gear, the switch gear, the generators and all of that. And that gets to be quite expensive. What you see in front is the current construction of the next phase of 13.2 megawatts that's being built in 4 modules of 4.4 megawatts. And you can see it's built with steel frames, and it's got a concrete slab, which means there's no raised floor. The roof is concrete because it needs to hold the air handling units that sit on the roof. And it's a much simpler construction, right? Much easier to build, less expensive. And then we have what we call hot aisle pods. So this is a picture of a pod in the original data center. The new one will look exactly like this. So what it is here are the server racks, right? And there are server racks on the other side. You see server racks on that side. And the cold air is on here and the other side of that. This door opens into what we call the hot aisle. And the hot aisle is enclosed. So when the door's closed, no hot air comes in. So that's what I mean by hot aisle isolation. It's completely isolated. You don't want the hot air to mix in with the cold air that the servers are drawing. So then typically what happens is we push cold air down here, and then the servers push goes through the servers, it gets hot, and then the hot air gets sucked up and pushed out the top. Okay, so that's the technique. In the original design, we were pushing cold air down, and then we had another set of fans in the air handling units pulling the air out. We did some airflow analysis and realized that we didn't need 2 sets of fans, that there are fans in the servers too. So we just push the cold air down and then rely on the fans in the servers and the pressure difference between the 2 sides to draw the hot air up and out of the data center floor. There's no raised floor, there's no chillers. We used to have the adiabatic coolers that you saw in the video in the original Dublin. don't need them. So there's absolutely no water used in the new Dublin design and one set of fans. So that has helped us improve our efficiency by a very large amount. You saw the IT packs in the video. So let me show you what's in them. What you see down here is the IT equipment. So there are 15 racks. Each rack has about 90 servers. So 15 times 90 in that. On top of that is the air handler with the fans that sucks out the hot air. And there are two other pieces so these 4 pieces together create a modular data center. So here's the IT part. There's the air handling unit. And this is the evaporation unit that has the media that you wet to provide additional adiabatic cooling. So on a typical day, and of course this is a picture was taken during the installation. So when everything is done, these two this all comes together. So the cold air comes in from that side, comes into the cold aisle of the IT part, goes through the servers, and then the air handler pulls it, and it goes out the top. Okay, that's a normal operation. When the temperature goes above a certain amount, let's say 30 degrees centigrade, I'm used to thinking Fahrenheit, so I've got to think to say what the centigrade is. Then what you do is you wet that evaporative media, and the amount of water is not a whole lot. The size of the pipe is like a garden hose, so it's not this big pipe that you see in a typical data center. So when the warm air comes in and goes through this media, there's about a 10 or 15 degree drop as it goes through that media. So if it's 95 out there, what the servers see is about 75 or 80. Okay, so on a hot day, that's what you do, and then it gets sucked out. Now servers don't like very cold weather either. So when the temperature goes below 50 degrees, which is 10 degrees centigrade, what you do is you saw in the video, there are these little things that let the outside air come in. You close those things a little bit, not completely open. Okay, that's like when you have in your car, you want to turn the amount of air conditioning air up or down, you close those things. So you draw in less outside air, and then there's the hot air coming out of the back of the servers. Instead of sending it all out of the IT pack, you recirculate that so through the mixing unit. And so when the hot air from the back of the server comes in and gets mixed with the outside air, you now bring up the temperature. Outside air is 50, you mix in the hot air, what the servers see is maybe 70 degrees. Okay? So those are the different operating modes of this IT pack. Now we've taken that same idea, not just on these IT packs, but a traditional building in our latest data center that's still under construction in